Imagine a world where machines can think, they learn, they create, just like humans do. This isn't science fiction. It's the future we're rapidly approaching, a future powered by artificial intelligence. But how did we get here? How did we go from clunky room-sized calculators to algorithms that can write poetry and predict the weather? The answer lies in the evolution of programming. It's a journey that began with punch cards and binary code, a far cry from the elegant languages and complex algorithms we use today. It's a story of innovation, perseverance, and the relentless pursuit of creating machines that can mimic and perhaps even surpass the power of the human mind. This is the story of how we went from ENIAC to AGI, from the first hesitant steps of programming simple calculations to the brink of artificial general intelligence. It's a story of how human ingenuity, fueled by curiosity and a drive to explore the unknown, has led us to the cusp of a new era. An era where the line between human and machine intelligence becomes increasingly blurred. The year is 1946. World War II had just ended, and the world was still reeling from the conflict. But amidst the aftermath, a revolution was brewing. A revolution that wasn't fought with guns and tanks, but with vacuum tubes and punch cards. This was the era of ENIAC, the electronic numerical integrator and computer, a colossal machine that occupied an entire room and weighed over 30 tons. ENIAC was a technological marvel, capable of performing complex calculations at speeds previously unimaginable. But behind this behemoth of a machine was a team of 6 brilliant women, the world's first programmers. These women, armed with nothing but their intellect and a profound understanding of logic, were tasked with taming this electronic beast. Their tools were not keyboards and monitors, but plugboards and switches. Their code wasn't elegant lines of text, but a complex dance of cables and connections. They were pioneers, venturing into uncharted territory, writing the first chapter in the history of programming. These women were instrumental in getting ENIAC up and running, developing the techniques and methodologies that would form the foundation of modern programming. Their work, often overlooked, laid the groundwork for the digital revolution that would follow. They were the unsung heroes who breathed life into the first electronic computer, setting in motion a technological tsunami that would forever change the world. In the beginning, there was machine code, a language of ones and zeros directly understood by the computer but utterly incomprehensible to humans. Programming in machine code was a tedious and error-prone process, requiring an intimate knowledge of the computer's hardware. But as computers evolved, so did the languages used to program them. Assembly languages emerged, offering a slightly more human-readable way to interact with these machines. Mnemonics replaced binary code, making it easier for programmers to write and understand instructions. However, the real breakthrough came with the advent of high-level programming languages. Fortran, or formula translation, developed in the 1950s, was a game-changer. It allowed programmers to write code that resembled mathematical formulas, making it easier to develop scientific and engineering applications. COBOL, or Common Business-Oriented Language, soon followed, catering to the needs of the business world. These high-level languages abstracted away the complexities of the underlying hardware, allowing programmers to focus on solving problems rather than wrestling with the intricacies of machine code. This marked a significant shift in the world of programming, making it more accessible and paving the way for the development of more sophisticated software. As the 1970s dawned, a new programming language emerged from Bell Labs, poised to revolutionize the computing landscape. This language was C, a powerful and elegant creation that combined the low-level control of assembly language with the expressiveness of high-level languages. C's strength lay in its ability to interact directly with hardware while still providing a relatively human-readable syntax. This unique combination made C the language of choice for system programming. Operating systems, the heart of any computer, demanded both efficiency and fine-grained control over hardware resources. C excelled in this domain, and its influence is evident even today in the architecture of modern operating systems. C was instrumental in the development of Unix, another groundbreaking innovation of the 1970s. Unix, a powerful and portable operating system, embraced the philosophy of modularity and simplicity. It provided a fertile ground for C to flourish, and together they formed a formidable duo that would shape the future of computing. The combination of C and Unix proved to be incredibly influential. Unix-like operating systems, inspired by the original Unix principles, are now ubiquitous, powering everything from smartphones to supercomputers. C's legacy lives on in these systems, a testament to its enduring power and flexibility. The lessons learned from C and Unix continue to guide the development of modern programming languages and operating systems. While C provided a powerful tool for system programming, a new paradigm was emerging that would change how software was designed and built. This paradigm was object-oriented programming, or OOP, and it offered a fundamentally different way of thinking about software development. OOP shifted the focus from procedures to objects, encapsulating data and behavior within self-contained units. This approach mirrored the real world more closely, where objects interact with each other to achieve a desired outcome. Languages like Simula and Smalltalk pioneered this concept, introducing ideas like classes, objects, inheritance, and polymorphism. Smalltalk, in particular, championed the OOP paradigm, demonstrating its power and elegance. It provided a complete programming environment built around OOP principles, showcasing the benefits of this approach in developing complex software systems. The rise of OOP marked a significant shift in software development. It allowed programmers to break down complex problems into smaller, more manageable objects, making code more reusable, maintainable, and scalable. This new way of thinking paved the way for the development of large, complex software systems that power our digital world today. The 1980s witnessed a profound transformation in the computing landscape with the advent of personal computers. No longer confined to research labs and universities, computers were now becoming accessible to the masses, entering homes and offices around the world. This democratization of computing was fueled by the emergence of affordable and user-friendly personal computers. With this new wave of personal computing came a need for a programming language that was both easy to learn and powerful enough to harness the capabilities of these machines. BASIC, an acronym for Beginner's All-Purpose Symbolic Instruction Code, emerged as the answer to this need. Developed in the 1960s, BASIC was designed with simplicity and ease of use in mind. Its straightforward syntax and intuitive commands made it an ideal language for beginners, especially young learners taking their first steps into the world of programming. BASIC became the gateway for a generation of programmers, sparking a passion for coding in countless individuals. The proliferation of personal computers, coupled with the accessibility of BASIC, led to an explosion of creativity. Hobbyist programmers, empowered by these new tools, wrote countless programs, games, and applications, pushing the boundaries of what was possible with these early machines. This era marked the beginning of a new era of personal empowerment through technology, where anyone with a computer and a bit of curiosity could learn to code and create their own digital worlds. The World Wide Web programming for a connected globe. The 1990s ushered in an era of unprecedented connectivity with the birth of the World Wide Web. The Internet, once a niche network used primarily by researchers and academics, was rapidly evolving into a global phenomenon, connecting people and information like never before. This digital revolution was fueled by the emergence of the World Wide Web, a system for accessing and sharing information over the Internet. At the heart of this revolution was HTML, the hypertext markup language. HTML provided a simple yet powerful way to create and structure web pages, using tags to define elements like headings, paragraphs, images, and links. This simple markup language, accessible to anyone with a text editor, democratized the creation of content, allowing individuals to share their thoughts, ideas, and creations with a global audience. The beauty of HTML lay in its simplicity and platform independence. Web pages created with HTML could be viewed on any computer with a web browser, regardless of its operating system or underlying hardware. This universality was key to the rapid adoption of the World Wide Web, breaking down the barriers of proprietary systems and connecting people across geographical and technological divides. The emergence of the World Wide Web and HTML marked a turning point in the history of programming. It shifted the focus from desktop applications to web-based applications, opening up a new frontier for programmers to explore. This new era demanded new languages, tools, and approaches tailored to the unique challenges and opportunities of the web. Java, JavaScript, and the rise of web applications. As the World Wide Web evolved, so did the demand for more dynamic and interactive web experiences. Static web pages, while sufficient for displaying information, lacked the ability to engage users in meaningful ways. This need for interactivity led to the development of new programming languages specifically designed for the web. Java, with its promise of write once, run anywhere, emerged as a powerful contender in this new landscape. Its platform independence, achieved through the use of a virtual machine, made it ideal for the diverse ecosystem of the Internet, where web servers and user devices could vary widely in their hardware and operating systems. Java's object-oriented nature and robust libraries made it suitable for developing complex web applications. JavaScript, often confused with Java despite their vastly different natures, took a different approach. Designed to run directly within web browsers, JavaScript brought interactivity to web pages, allowing developers to create dynamic content, handle user input, and respond to events in real time. JavaScript's lightweight nature and tight integration with HTML made it an instant hit, and it quickly became the de facto language for front-end web development. The combination of Java and JavaScript unlocked a new era of web applications. Java, running on servers, provided the back-end logic and data management, while JavaScript, running in browsers, handled the user interface and interactivity. This client-server architecture became the foundation for countless web applications, from online shopping platforms to social media networks. The open source movement, collaboration and innovation in the digital age. As the Internet connected people and ideas, a new philosophy of software development began to take hold: open source. This movement, fueled by the collaborative spirit of the Internet, challenged the traditional model of proprietary software, where code was closely guarded and shared only under restrictive licenses. Open source software, in contrast, embraced the principles of transparency, collaboration, and community-driven development. Source code was made freely available to anyone to use, modify, and distribute, fostering an environment of innovation and shared learning. Projects like Linux, a free and open-source operating system, and Apache, a web server software, demonstrated the power of this approach. The open-source movement had a profound impact on the evolution of programming. It broke down barriers to entry, allowing anyone with an internet connection to access and learn from high-quality code. This led to a rapid proliferation of open-source libraries, frameworks, and tools, empowering developers to build software faster and more efficiently. The collaborative nature of open source fostered a culture of sharing knowledge and best practices, accelerating the pace of innovation. This spirit of openness and collaboration would later play a crucial role in the development and advancement of artificial intelligence. While programming languages were evolving at a rapid pace, a parallel quest was underway: the pursuit of artificial intelligence. The dream of creating machines that could think, learn, and reason like humans had captivated the imaginations of scientists and philosophers for centuries. But it was in the mid-20th century, with the advent of electronic computers, that this dream began to take on a tangible form. In 1950, Alan Turing, a brilliant British mathematician and computer scientist, published a seminal paper titled Computing Machinery and Intelligence. In this groundbreaking work, Turing proposed a test, now known as the Turing test, to determine if a machine could exhibit intelligent behavior indistinguishable from that of a human. The Turing test, despite its simplicity, sparked a wave of research in the field of artificial intelligence. It provided a clear, albeit controversial, benchmark for measuring machine intelligence, challenging researchers to create machines that could convincingly mimic human conversation. Early AI research focused on symbolic reasoning, attempting to represent human knowledge and logic using symbols and rules that computers could manipulate. These early AI systems, while limited in their capabilities, showed promise in solving specific problems, such as playing checkers or proving mathematical theorems. The dream of creating thinking machines was alive, fueled by the rapid advancements in computing technology and the tireless efforts of researchers around the world. Building on the foundations of symbolic reasoning, researchers in the 1970s and 1980s developed expert systems, a new breed of AI programs designed to solve problems in specific domains by mimicking the knowledge and reasoning of human experts. These systems relied on a knowledge base, a collection of facts and rules representing expertise in a particular field, and an inference engine which used this knowledge to answer questions, make recommendations, or solve problems. Expert systems showed promise in a variety of fields, from medical diagnosis to financial analysis. One notable example was Mycin, an expert system developed at Stanford University in the 1970s to diagnose bacterial infections of the blood. Mycin's ability to diagnose infections with an accuracy rivaling that of human experts generated considerable excitement about the potential of AI in medicine and other fields. However, despite the initial success of expert systems, limitations soon became apparent. These systems were brittle, struggling to handle situations outside their narrow domains of expertise. They lacked common sense reasoning and the ability to learn from new experiences. The hype surrounding AI, fueled by overly optimistic predictions, led to disappointment when these limitations became evident. This period of disillusionment, marked by reduced funding and interest in AI research, became known as the AI winter. The AI winter, though a setback for the field, proved to be a valuable learning experience. It forced researchers to re-evaluate their approaches, to acknowledge the limitations of symbolic AI, and to explore new paradigms that could overcome these challenges. The seeds of a new revolution in AI were sown during this period of introspection, a revolution that would be fueled by the power of data and the resurgence of artificial neural networks. While expert systems struggled to capture the nuances of human intelligence, a different approach to AI was quietly gaining traction. This approach, inspired by the structure and function of the human brain, explored the potential of artificial neural networks. These networks, composed of interconnected nodes or neurons organized in layers, aim to mimic the brain's ability to learn from data and make predictions. The concept of artificial neural networks had been around since the 1940s, but early attempts to train these networks were met with limited success. The lack of efficient training algorithms and the limited computational power of the time hindered progress in this area. However, the theoretical foundations of neural networks continued to intrigue researchers, who saw their potential to overcome the limitations of symbolic AI. In the 1980s, a breakthrough came with the development of the backpropagation algorithm. This algorithm provided an efficient way to train multi-layered neural networks by propagating error signals back through the network, adjusting the weights of connections between neurons to improve the network's accuracy in performing a given task. This breakthrough re-energized the field of neural networks, leading to renewed interest and investment in this promising area of AI. Despite the promise of backpropagation, training large neural networks remained computationally expensive, and the availability of data, crucial for training these networks, was still limited. The stage was set for another leap forward, a leap that would be fueled by the exponential growth of data and computing power in the decades to come. Deep learning unleashing the power of data. The 21st century witnessed an unprecedented explosion of data. The proliferation of internet-connected devices, sensors, and social media platforms generated an overwhelming amount of digital information, creating what came to be known as the era of big data. This data deluge, initially a challenge to manage and analyze, proved to be a boon for the field of artificial intelligence, particularly for neural networks. With access to vast amounts of data and increasingly powerful computers, researchers could now train deeper and more complex neural networks, leading to the emergence of deep learning. Deep learning algorithms, characterized by their use of multiple hidden layers of neurons, proved to be exceptionally adept at learning complex patterns and representations from raw data. Deep learning revolutionized the field of artificial intelligence, achieving breakthroughs in areas that had long stymied traditional AI approaches. Image recognition, speech recognition, natural language processing, and machine translation all witnessed dramatic improvements thanks to the power of deep learning. The ability of these algorithms to learn directly from data, without the need for hand-coded rules, opened up a world of possibilities for AI applications. The rise of deep learning marked a turning point in the quest for artificial intelligence. It demonstrated the power of data-driven approaches, fueled by the availability of massive datasets and the computational resources to process them. This new era of AI, driven by deep learning, continues to evolve at an astonishing pace, pushing the boundaries of what machines can achieve and fundamentally reshaping our relationship with technology. AI today, a new era of machine intelligence. Today, artificial intelligence is no longer a futuristic concept confined to science fiction. It's here, it's real, and it's rapidly transforming our world. AI powers our smartphones, personalizes our online experiences, assists doctors in diagnosing diseases, and is even starting to drive our cars. This new era of machine intelligence is driven by the remarkable progress made in areas like machine learning, deep learning, and natural language processing. One of the most visible manifestations of AI's progress is the rise of AI assistants like Siri, Alexa, and Google Assistant. These voice-activated companions have become ubiquitous, seamlessly integrated into our daily lives. They can answer our questions, set reminders, play music, control our smart homes, and even engage in casual conversation, albeit with varying degrees of naturalness. But AI's impact extends far beyond these consumer-facing applications. In healthcare, AI is assisting doctors in diagnosing diseases earlier and more accurately, analyzing medical images to detect anomalies, and even personalizing treatment plans based on a patient's genetic makeup and lifestyle. In finance, AI is being used to detect fraudulent transactions, assess credit risks, and provide personalized financial advice. The advancements in AI have been nothing short of remarkable. Tasks that were once considered the exclusive domain of human intelligence, such as recognizing faces, understanding natural language, and playing complex games, are now being performed by AI systems with impressive and sometimes superhuman accuracy. This rapid progress has sparked both excitement and apprehension, raising profound questions about the future of work, the ethics of AI, and the very nature of intelligence itself. From language to vision, AI is expanding horizons. One of the most significant breakthroughs in recent years has been in the field of natural language processing. Large language models, trained on massive datasets of text and code, have demonstrated an uncanny ability to understand and generate human-like language. These models can translate languages, write different kinds of creative content, and answer your questions in an informative way, even if they are open-ended, challenging, or strange. AI's prowess extends beyond language to the realm of vision. Computer vision, a field that enables computers to see and interpret images, has also witnessed remarkable progress thanks to deep learning. AI systems can now recognize objects' faces and even emotions with astonishing accuracy. This technology is being deployed in a wide range of applications, from self-driving cars that can see and navigate their surroundings to security systems that can identify individuals and detect suspicious activities. AI is also making its mark in robotics, enabling machines to perform tasks that were once considered too complex for automation. Robots are now being used in manufacturing, logistics, healthcare, and even homes, performing tasks ranging from assembling intricate electronic components to assisting surgeons in delicate surgical procedures. The advancements in AI have blurred the lines between science fiction and reality. Machines can now perform tasks that were once thought to be the exclusive domain of human intelligence, and they're doing so with increasing sophistication. As AI continues to evolve at an unprecedented pace, it's reshaping our world in profound and often unpredictable ways, challenging our assumptions about what machines can do and raising fundamental questions about the future of our species. Despite the remarkable achievements in artificial intelligence, a grand challenge remains: achieving artificial general intelligence, or AGI. AGI, often referred to as strong AI, represents the holy grail of AI research, the creation of machines that possess human-level intelligence across a wide range of tasks, capable of learning, reasoning, and adapting to new situations with the same flexibility and ingenuity as humans. Current AI systems, while impressive in their specialized domains, are still far from achieving this level of generality. They excel at tasks they are specifically trained for, but they lack the ability to transfer their knowledge and skills to new and unfamiliar situations. A chess-playing AI, for example, cannot effortlessly switch to writing poetry or designing a scientific experiment. The quest for AGI is fraught with challenges. Researchers are exploring various paths, from scaling up existing deep learning architectures to developing entirely new paradigms that incorporate reasoning, common sense understanding, and the ability to learn and adapt autonomously. Some believe that simply increasing the size and complexity of neural networks combined with massive amounts of data will eventually lead to AGI. Others argue that fundamentally new approaches are needed, approaches that draw inspiration from cognitive science, neuroscience, and even philosophy. The path to AGI is uncertain, with no guaranteed roadmap to success. It's a journey of exploration, experimentation, and continuous learning, driven by the fundamental human desire to understand and recreate the very essence of intelligence. As we venture closer to the possibility of AGI, we must confront a myriad of ethical considerations that come with creating machines potentially capable of surpassing human intelligence. The development of AGI is not merely a technical challenge, it's a profound societal and philosophical undertaking demanding careful consideration of its potential impact on humanity. One of the most pressing concerns is ensuring the alignment of AGI with human values. How do we ensure that these powerful machines, capable of making decisions with far-reaching consequences, act in ways that benefit humanity and align with our ethical principles? The challenge lies in defining these values and translating them into a form that machines can understand and act upon. Job displacement is another significant concern. As AGI systems become increasingly capable, they have the potential to automate a wide range of jobs currently performed by humans, leading to economic disruption and societal upheaval. Addressing this challenge requires proactive measures such as retraining programs for displaced workers and exploring new economic models that adapt to an AI-driven workforce. The development of AGI raises fundamental questions about the nature of consciousness, sentience, and the very definition of intelligence. If we succeed in creating machines that can think and learn like humans, what rights and responsibilities do we owe them? These are not merely hypothetical questions to be pondered in the distant future. They are pressing ethical dilemmas that demand careful consideration as we navigate the uncharted waters of AGI development. AI assistants, the always-on companions. The next decade will see AI assistants transcend their current role as helpful but limited companions. Imagine a world where your AI assistant knows your preferences better than you do, anticipating your needs before you even articulate them. These sophisticated assistants will evolve beyond simple voice commands, seamlessly integrating into our lives through augmented reality, wearable technology, and even brain-computer interfaces. This future promises a world of unprecedented convenience and personalization. Need to schedule a meeting? Your AI assistant will coordinate with others, finding a time that works for everyone and automatically booking the meeting room. Planning a trip? Your AI assistant will handle everything from flights and accommodation to itinerary suggestions tailored to your interests and budget, all while ensuring you get the best deals and avoid potential travel hiccups. The healthcare industry is poised for a revolution driven by AI. Imagine a world where AI assistants monitor our health continuously, analyzing data from wearable sensors and alerting us to potential issues before they escalate. These assistants will become our personal health advocates, providing personalized health advice, reminding us to take medications, and even connecting us with healthcare professionals when needed. Beyond personal assistance, AI will permeate various industries, automating tasks, augmenting human capabilities, and driving innovation at an unprecedented scale. In manufacturing, AI-powered robots will collaborate with human workers, optimizing production lines and creating highly customized products tailored to individual customer needs. In transportation, self-driving cars will become increasingly common, reducing accidents, easing traffic congestion, and transforming our cities. Reshaping industries, reshaping lives. Education too will be transformed by the rise of AI. Personalized learning platforms powered by AI will adapt to each student's unique learning style and pace, providing customized lessons and feedback. Imagine a world where every student has access to a personal AI tutor, available 24/7 to provide guidance, answer questions, and help them achieve their full potential. The job market, as we know it, will continue to evolve. While AI will undoubtedly automate many existing jobs, it will also create new opportunities that we can only begin to imagine. The key lies in adapting our skills and embracing lifelong learning, focusing on areas where human creativity, critical thinking, and emotional intelligence will remain invaluable assets. AI has the potential to accelerate scientific discovery, helping us solve some of humanity's most pressing challenges. Imagine AI systems analyzing vast data sets of scientific literature, identifying promising research avenues, and even designing and conducting experiments, freeing up human scientists to focus on the big questions and interpret the results. From developing new drugs and therapies to combating climate change, AI will become an indispensable tool in our quest to understand and improve the world around us. However, this future is not without its challenges. As AI becomes more powerful and pervasive, we must address the ethical implications of its development and deployment. Ensuring fairness, transparency, and accountability in AI systems will be crucial in preventing bias and discrimination. We must also grapple with the potential impact of AI on privacy and security, establishing clear guidelines and regulations to protect individual rights. The legacy of code from humble beginnings to boundless potential. Our journey from ENIAC to the cusp of AGI is a testament to the boundless potential of human ingenuity. From the laborious process of programming with punch cards and wires to the elegance of modern programming languages, we've witnessed an extraordinary evolution in how we interact with machines. We've taught them to calculate, to process information, to learn, and perhaps soon, to think in ways that rival our own. This journey is not just about technological advancement, it's about the human spirit of curiosity, our relentless pursuit of knowledge, and our desire to create tools that extend our reach and understanding. The pioneers who programmed ENIAC, the developers who crafted the first high-level languages, the countless programmers who contributed to open-source projects, they all played a part in building the foundation upon which the AI revolution stands. As we stand on the brink of a new era, it's worth reflecting on the profound impact programming has had on our world. It has transformed how we communicate, how we work, how we learn, and how we entertain ourselves. It has connected us across continents, democratized access to information, and empowered individuals to create and innovate in ways never before imaginable. The legacy of code is not just lines of instructions for machines, it's a testament to the power of human creativity and our ability to shape the world around us. It's a legacy that will continue to evolve as we push the boundaries of what's possible with artificial intelligence. Shaping the future, a shared responsibility. The future of AI is not preordained, it's a future we are actively shaping through the choices we make today. As AI becomes more integrated into our lives, it's imperative that we approach its development and deployment with a sense of shared responsibility. We must ensure that AI benefits all of humanity, not just a select few, and that it aligns with our values and aspirations for a better future. This requires a multifaceted approach involving collaboration between AI researchers, policymakers, ethicists, and the public. We need to establish clear ethical guidelines for AI development, ensuring that these systems are designed and used responsibly with appropriate safeguards in place to prevent unintended consequences. Education is paramount. We need to equip future generations with the knowledge and skills to navigate an AI-driven world, fostering critical thinking about AI's potential benefits and risks. We must also address the societal impact of AI, ensuring that its benefits are shared equitably and that we mitigate potential negative consequences such as job displacement and algorithmic bias. The journey from ENIAC to AGI is a testament to the transformative power of technology. But as we venture further into the uncharted territory of artificial intelligence, we must remember that the future is not something that happens to us, it's something we create. Let's ensure that the future of AI is one where humans and machines coexist and collaborate, creating a world that benefits all.